they're all distance vector routing protocols. They all make their decisions on how far that destination network is and in which direction we have to go to get there. That distance is based on hop count. Hop count meaning the number of routers we have to hop through to get to that destination network. So is it 1 router hop, 3 router hops, 5 router hops? The path with the least number of router hops is the shortest path, and that's the path we will end up taking. Vector is referring to the direction. Is it out this interface, out that interface, or maybe that one over there? RIP, in all its flavors, reminds me of a street sign. A street sign that simply says, if you're going to that place, go that way. And it's X number of miles. That's about it. You have very little visibility into the terrain or how far it truly is. For example, is that place you're going to in New York City where a New York block is relatively huge compared to your hometown where a block is, oh, well, there's the next block and there's the next block. So you don't have the visibility into truly how far it is. You just know how many hops it is away. And as a result, RIP, because it really doesn't care about anything else, can make some very bad decisions. And we can see an example of that here. When traffic flows from PC1 to PC2, which path is it going to take? Is it going to cross the 100 megabit per second link? Or is it going to take the scenic route? In most cases, folks, if you're in a hurry, the scenic route is not the path you will take. But in this case, the scenic route is the quicker path based on speed. We have 1 gig links. And even though it's 3 1 gig links, that is way faster than one 100 meg link. But RIP is making its decision on router hops, not how fast it is to get there based on, for example, bandwidth. So what happens in this case? RIP chooses that 100 meg link because it's only how many router hops away? Well, from this router's perspective, right here, we have 1 hop. Whereas this way, we have 1 hop, 2 hops, 3 hops. So we have 1 versus 3. 1 is lower than 3. Therefore, RIP in this case chooses the suboptimal path to route the traffic over. But that's the way it's designed. That's the way it works. So it's important when you are implementing RIP, you factor in these design restrictions or design constraints to make sure you don't end up in this type of situation. With that said, though, it's important to realize that RIP is designed for really small environments. You're not going to use it in a large environment that you plan on scaling to even larger scaling to an even larger environment at a future time. When we're comparing RIPng and we're trying to understand, what is it all about? Well, not a whole lot has changed from its predecessors, such as RIP version 2. One of the big differences is that RIPng is routing for IPv6 traffic, whereas RIP version 2 is for IPv4. The UDP port numbers are pretty close to being the same. They're not exactly the same, but they're pretty close. With RIP version 2, we had UDP port 520 for communication purposes, and RIPng, it's port 521. The multicast address here is rather interesting, and I like what they've done with it. With RIP version 2, since it's IPv4 related, we're dealing with IPv4 multicast addresses, like we see here. And if we compare that over to our RIPng multicast address, that RIPng multicast address is based on an IPv6 address, so it's very difficult to keep that the same as IPv4. But what they did is they kept the 9 the same. And I like that. That makes it easy on us to remember what the multicast address is. It's still 9 regardless of what we're doing. Variable length subnet masking is supported by both. Thank goodness, because without variable length subnet masking, we'd be in a world of hurt in today's environments where we do a lot of subnetting and we support different lengths of subnet mask. So with IPv6, Might have a /64 or /63 or /62. It all depends. In your IPv4 networks, you're definitely subnetting, and you'll have different mask lengths there. So variable length subnet masking, very important. The metric is based on hop count, and there's still a maximum number of hops, and that is 15. So just because it's IPv6 and it's supposed to be better than IPv4 doesn't mean the routing protocol, such as RIPng, is any better than its predecessor. We're still maxed out at 15 hops, and if the destination network is 16 or more hops away, it is classified as being unreachable. Administrative distance, still the same, 120. What's the administrative distance of EIGRP? It's 90. OSPF, 110. And that's regardless of whether it's EIGRP for IPv4 or IPv6 or OSPF v2 or v3. Those are their administrative distances. Likewise here. It's 120, regardless of whether it's for IPv6 or IPv4. Routing updates, still every 30 seconds. That hasn't changed. So we constantly bug our neighbors every 30 seconds to tell them, this is what I know. This is what I know. And if there is a topology change because of triggered updates, we'll let them know right away. And then authentication is supported, and that is a must. I would not implement a routing protocol nowadays without authentication, simply because I want to make sure my router only accepts routing information from authentic sources. We don't want to accept route advertisements from rogue routers.